This lecture is going to be on climate controls, and we're going to look at, or as we continue studying the climate system, we're going to look at the factors that influence the climate system. Here we can see that the controls on climate, that we generally attribute seasonal temperature and precipitation patterns to the influence of a combination of 6 climatic controls. Latitude. What latitude is highly influential? Land and water, geographic position and prevailing winds, mountains and highlands, ocean currents, and pressure and wind systems. We will examine all of these factors and more. These two maps, or pictures here, kind of help illustrate that. So let's talk latitude first. Right, the closer one is to the equator, the greater the insolation they get on average throughout the calendar year. So even though as you move towards, right, when we talk about our summer solstice in the northern hemisphere, even though 23.5 degrees north gets the greatest insolation, that's only for a short amount of time. That's only during June, and it's important to realize that the equator on average has the highest or warmest conditions due to insolation. And then land and water, right? The closer you are to a body of water, and the greater that water is going to have on influencing local climate. For example, a West Coast city would be buffered by the North Pacific Ocean as opposed to us in the mid-continent, as Chicago is influenced by the land. Land is going to heat up a lot more readily, a lot more easily than water. Water has what we call a thermal inertia to it. It resists, has a higher specific heat. So land and water depends on where it's located. So Chicago is going to heat up differently than a coastal city. Moving on, geographic position and prevailing winds. This is a wind map. That winds coming off of, say, a body of water are also going to be influencing the temperature and precipitation conditions. So geographic position and prevailing winds, the winds. We can't ignore winds are going to be bringing the temperature conditions and the potential for precipitation, both of which are climatic factors. Mountains and highlands. We should know by now that at elevation, as I rise up in our atmosphere, in our troposphere, it gets cooler. So in a city that's at a higher elevation, a mountain town or a mountain city, is going to be cooler on average than a town that would be closer to sea level. Simply based on elevation is going to be cooler. And ocean currents. And these are ocean currents. This is an ocean current map. I want you to realize that warm currents are noted in red and blue currents are considered cold. So blue, cold, red, warm. And warm currents are going to be delivering, right, warmer water is going to influence the air above it. So we can't ignore the ocean currents. This is the reason why, even though that Europe is a higher latitude than the mainland United States, it actually has warmer average conditions because of the warm ocean currents, right? The Gulf Stream turns into the northern Atlantic current that actually gives off its heat. So Europe and northern Europe actually are, let's just say, about the same conditions, even though they're farther north in terms of latitude. And then lastly, pressure and wind systems. That there's a lot of wind systems, that we've got all these different wind factors working simultaneously, that all 6 of these climatic factors act and influence the Earth's climate altogether. But we can't ignore the sun. That radiative forcing is a very important part of this, right? We have sunlight coming in, and we have some of it that's being absorbed and some of it being reflected. So let's look at that. In climate science, radiative forcing or climate forcing is defined as the difference of insolation, right, incoming solar radiation, absorbed by the Earth and the energy radiated back to space. A positive forcing, right, more incoming energy, warms the Earth system. An example of what we call a positive forcing would be greenhouse gases, right, primarily carbon dioxide. This is kind of the signature for warming of the planet. It holds on to heat. But remember, greenhouse gases can also involve water vapor as well. So anything that holds on to heat, where the atmospheric heat energy is trapped and the temperatures increase. And remember, this isn't completely a bad thing. The greenhouse effect is very good, right? Liquid water on the Earth's surface is a very good thing, very good for life. A negative forcing has the opposite effect. As a positive forcing, where the Earth system would cool down. A negative forcing includes an aerosol. We've talked about particulates, and we'll look at that a little bit further, a little bit more here. An aerosol. So we'll call these particulates and cloud cover. where insulation is reflected back into space, leading to a net cooling. So we can have these influences that we're called radiative forces. If heat is trapped and it continues to warm, we call that a positive forcing. If heat is reflected, we call that a negative forcing. And those have two opposite effects. If it's trapped, it leads to a temperature increase. If they're reflected, it leads to a net loss of temperature or cooling. So here we have just kind of a picture that puts a lot of different processes together. That a small change in any variable can have a profound effect on other variables of the Earth's surface. And here, just kind of an idea that the solar cycle is every 11 years, and it can have mild changes in how much energy that it drives towards the Earth. However, one event can change the world. If we look at a volcanic eruption, this here is Mount Pinatubo, it releases all this dust and debris into the atmosphere that travels, then blankets the Earth. And even though it's spread out, these particulates reflect sunlight. It reflects sunlight, so therefore it leads to a cooling feature, right? And that would be a negative forcing, as mentioned here. So these lead to negative forcing. So a volcanic eruption, one volcano can change the world. And these particulates, these aerosols, blanket the Earth, and they do eventually dissipate. They settle out of the Earth generally in the form of precipitation. They become condensation nuclei. And we'll do a little lab activity on that. And also asteroid impacts. One might think, well, this asteroid impact, you think of it as like killing everything, but that's not necessarily true. An asteroid impact really comes down to it sends tremendous amounts of debris into the atmosphere, much like that of a volcano, that both lead to an increase in aerosols in the atmosphere. The aerosols are transported in the atmosphere by wind currents and encircle the planet. The aerosols reflect incoming solar radiation, thus decreasing the amount of energy reaching the Earth. Aerosols can become condensation nuclei and cloud seeds, further reflecting insolation. Volcanic eruptions and impacts have a positive feedback, which further drive global climate into cooler conditions. A positive feedback doesn't mean it's a positive outcome. The positive is simply the direction in which it's changing a feedback system. In other words, a positive feedback amplifies the situation, whereas a negative feedback is a stabilizing feature. So we can refer to these feedback loops as what is happening. A negative feedback loop, this is what causes stability in a system. It offsets the variable that is changing. An example, a rise in cloud cover on the Earth's surface due to warming can increase the amount of sunlight being reflected back into space, thus decreasing the amount of heat energy that's added to the Earth system. So cloud cover becomes a negative feedback loop that redirects incoming solar radiation. So it kind of balances. It stabilizes the system by offsetting the variable. It's a stabilizer. Where a positive feedback loop, this causes instability in a system by increasing the magnitude of the variable that is changing. For example, during an ice age, continental glacial ice reflects incoming solar radiation, driving the Earth system to even further cooler conditions. So a positive feedback doesn't mean it has a positive outcome. It's simply amplifying the variable that's changing. Whereas a negative feedback doesn't have a negative effect. It actually is a good thing because it balances or stabilizes the system. Okay, moving on. So here we'll look at Keeling curves, and everything moving forward is going to be all about data. Everything's about the data here. We'll begin studying climate systems based on what is happening to the chemistry of the atmosphere. Here we see that carbon dioxide is no doubt increasing in our atmosphere. And this is the famous Keeling curve, that the Keeling curve is showing that this carbon dioxide concentration is increasing. And it has been very, let's just say at a relatively steep angle in recent history. And we'll be talking about why is the Keeling curve so important? Well, here's why. This is studied, this is measured in Hawaii, and here's why. It's so isolated, right, in the Pacific Ocean. Because it's isolated, we say that the air in and around the North Pacific is, let's just say it's a fair representation of the Earth's current state. It's an average condition, that it's not located in the U.S. where it might be close to, a lot of industry where carbon dioxide is being emitted into the atmosphere. Instead, it's pretty isolated. Therefore, we call this a relatively good indicator of what the atmosphere is doing. And then last but not least, and there's where we start getting into the data. The data is what's going to tell the story. Since the Industrial Revolution, fossil fuel usage has led to dramatic increases in carbon dioxide levels, unprecedented in Earth's recent 400,000 years, right? See the graph. So here's what we're looking at. If I look at my x-axis here, if I go back in time, this goes back to 400,000 years ago. But remember, the Earth is, well, let's just say, several billion years old. But this is only looking at 400,000 years. So let's not make it seem like, let's get some perspective here. We will have to begin looking at numbers, graphs, and analyzing the effects of changing the atmospheric chemistry before we can begin to make sense of what is really going on. We will be using climate models to address the quantitative data. And in this case, we're going to start using numbers. We're going to start looking at graphs and trying to make sense as to what is going on. Because if really this graph, it's trying to show you that for 650,000 years, if we go back to the beginning, to the origin, atmospheric carbon dioxide had never been above this line. And yet, it's well above that line now. So the question is, does by increasing the carbon dioxide in the atmosphere itself, is that going to lead to increased temperatures on Earth, right? Warming of the Earth is taking place, but is carbon dioxide, and once again, since the Industrial Revolution, is anthropogenics a viable explanation as to why the planet is warming by the fossil fuel, by the carbon dioxide input into the atmosphere? And that's what we're studying.